actually having a 0 in between there. This is using a t-test. So you know that the variable EGFR is not normally distributed. You don't want to use the t-test. You want to use the Wilcoxon rank sum test. So you say rank sum EGFR 1 by nephrotoxicity. And it's also agreeing that at the time these patients were initiating treatment, there was no significant difference in the estimated glomerular filtration rate. Now let's ask this same question after treatment. T-test after treatment. Was there a significant difference in the estimated glomerular filtration rate after these patients were treated with tenofovir disoproxil fumarate? P-value is less than 0.05. So this just tells you that there was a statistically significant difference in the EGFR. Those that ended up with nephrotoxicity had a mean EGFR of 66, while those that did not have nephrotoxicity had a mean EGFR of 123. The difference was as much as 57 micromoles per liter. If you want to check this difference using the confidence interval, you would notice that they are both on the right side of 0. Both above 0, this is showing a statistically significant difference. I also told you why the confidence interval is the better parameter to use to determine whether there was a statistically significant difference. And this is because it also tells you the magnitude of the difference. The difference between those that had nephrotoxicity and those that did not have nephrotoxicity would range from a minimum of 47, 48 to as much as 67. That's how different the estimated glomerular filtration rates would be. Now, since you know that the variable EGFR was not normally distributed, you can go ahead and do the rank sum test. So we say rank sum EGFR 4 by 6, not 6, at nephrotoxicity. And it's also showing that yes, there was a statistically significant difference. This difference that you are seeing was significant. Okay? This means that there was a statistically significant difference in the medians. The median EGFR after treatment was statistically different. So you can actually even check the median. Central EGFR 4, central 50, and that's the median for the EGFR 4. But if you say by sort, nephrotoxicity, you say separate the EGFR by those that had nephrotoxicity and those that did not have nephrotoxicity, and then determine their medians. You see that the median EGFR for those without nephrotoxicity was 127, or the median EGFR for those who ended up with nephrotoxicity was about 67. So there was a difference after treatment. What does this tell you? It tells you that those that ended up with nephrotoxicity had a lower EGFR, though they began with normal EGFR, while those that did not have nephrotoxicity had a high EGFR, and this difference was significant and could be attributed to the treatment that they had had. Is that okay? Yeah. This is basically usable when you are doing an analysis in two groups. Nephrotoxicity has two groups. It's those that had nephrotoxicity and those that did not have. Right? The same thing with sex. It had two groups. Those who were male and those who were females. So you can still see this code book, nephrotoxicity and sex, and it's telling you that nephrotoxicity had two groups. It had two numerical values. One was those without nephrotoxicity, two was those with nephrotoxicity. Same thing with sex. One, those that were female, and two, those that were male. Let's try to think of a situation where, for example, you want to use a variable as the grouping variable which has more than two groups. Let's give an example of a variable such as the treatment. So it's a code book treatment. What code book does basically tells you how the variable has been encoded. So treatment. When you look at the variable treatment, it has three numerical values. It has three possible values. One for drug code AZT, that's zidovudine. Two for the drug TDF, tenofovir disoproxil fumarate, and three for the drug stavudine. What would you do if you want to determine whether there was a difference in the estimated glomerular filtration rate of participants that were treated using three different drugs? At this point, I must tell you that this variable treatment, I just made it up. I just randomly selected the treatment. It wasn't there initially, so it might not give the exact result as it was, but I made this variable just so I can show you what you do in this case. So the null hypothesis for the test you want to do, which is the ANOVA, is that there is no difference in the mean eGFR regardless of the treatment. Remember, you have three groups. In this one, you had two groups. You said difference between two means. Here you are saying different among the three means. So in fact, the null hypothesis says that the mean eGFR is actually the same between AZT is equal to TDF, which is equal to D4T. Here is the null hypothesis. There is no difference. You must know that if there is a difference anywhere, either between AZT and TDF, or between TDF and D4T, or between AZT and D4T, if there is just one difference, it's going to signal that there is a significant difference. That's the null hypothesis of the ANOVA. All the means are equal. You can use the ANOVA if you have two or more groups. Okay? If you have two or more groups, the ANOVA is actually usable. So, how do you do it? You can say one way, because it's called the one-way ANOVA. You only have one variable that you're actually comparing as the variable in which you're using as a comparative. The grouping variable is just one, which is a treatment. So just say one way ANOVA to mean one variable. So one way, the outcome variable, eGFR 1, and then the exposure variable, treatment. And here it is. It has given you F statistic there, the mean squares, sum of squares, the degrees of freedom there, and it's actually giving you a p-value here. And the p-value is equal to 0.12. P-value of 0.12 simply tells you, which is above 0.05, tells you that there is no significant difference in the eGFR amongst the treatment groups. So those that were treated with TDF, those with D40, those with stavudine, all had the same EGFR before the treatment began. Is that okay? So, if you want to confirm this, after treatment, just change this, the variable EGFR. What was the GFR after treatment? It still tells you that there was not a statistically significant difference, but this is mainly because the variable TDF, D40 and stavudine was just made up. It wasn't there initially. It was just for me to demonstrate to you how you use the ANOVA. Again, ANOVA, the assumptions are very similar to the assumptions of the t-test, which is that the variables where the outcome variable was normally distributed, which means there are no extreme values or outliers, and that the medians and that the residuals are actually normally distributed, which is basically saying they are equivariance. It's called the assumption of heteroscedasticity. And then that the sample size was large enough and the sampling of the participants was random. Those are the assumptions that we actually consider in ANOVA. The most crucial is actually of the random sampling of the participants and that there were no extreme values. Now, you and I checked whether this variable EGFR4 and EGFR1 were normally distributed, and we know it's not normally distributed, so we know that the ANOVA, which is our parametric test, is not usable in this case. So what do? You use the alternative of the ANOVA, and this is called the Kruskal-Wallis H test. So it's a Kruskal-Wallis. This K-Wallis is Kruskal-Wallis. You say EGFR1 by So what this is saying is that is there a statistically significant difference in the median EGFR at the beginning of treatment, at the beginning of the study, amongst those treated with the 3 drugs? Was there a significant difference in the median? The null hypothesis is that median 1 is equal to median 2, which is equal to median 3, and so on and so forth. So median in stavudine was equal to the median in TDF, which was equal to the median in AZT. And the p-value you are going to get from here is 0.14. There was not a significant difference in the median EGFR beginning of treatment. Do the same after treatment. There was also not a statistically significant difference in the median. You can actually confirm this by even looking at the values of the medians themselves. So you can say, what was the median therefore? I sought treatment. You say centile EGFR. Centile, remember that this centile is coming from the centile, and the median is the 50th percentile, right? So the median is the 50th percentile number. So you say, I sought treatment, which is separate by treatment, or sort by treatment, and show me the 50th percentile number of EGFR in the 3 treatment groups. So this is the 50th percentile. You can actually put any percentile you want. You can actually even put 25 percentile and 75 percentile like this. 25, 75, which means it's going to be able to, it's going to show you the 25 percentile, the 50 percentile, and the 75 percentile. So just to make this a lot more lean, there it is. Tells you that the median EGFR1, amongst those treated with AZT was 130. Amongst those treated with TDF was 136, and those treated with D4T were 133. After doing the Kruskal-Wallis test, we were able to determine that this difference we are seeing here is not statistically significant. You are able to observe such kind of a difference even if there is not a significant difference. Is that okay? So what have we discussed today? We have discussed the ANOVA, when you use it, and the alternative test, the ANOVA. We've also revised the t-tests, when you use it, and the alternative of the t-test. In closing, I just want to show you why I was telling you that the ANOVA is basically an extension of the t-test. The ANOVA is an extension of the t-test. You use the t-test when you have two groups. When you have more than two groups, you use the ANOVA. In fact, we can actually do an ANOVA when you have two groups, and the answer you get is the same answer that you would get when you do a t-test. Basically, it's an ANOVA. T-test is basically an ANOVA with two groups. Okay? So, let me show you. ANOVA. You can say ANOVA or one way. Stick to what we have been using. One way, EGFR1 as X. There you go. Let me do the same thing using a t-test. T-test EGFR1 by X. So here is your p-value, the t-test. 0.2083. P-value for your ANOVA, 0.2083. The same. Get the sense? It's giving the same p-value in this case. Actually, when you come to regression, you would actually also discover that even if you were to do linear regression by sex, it would be able to show you the difference, exact same difference, exact same p-value by sex. So linear regression is also a generalization of the t-test and all the other statistical tests.